All right, next up, we're going to try to calculate delta G of reaction from Hess's law. So if you think back, you did this in Chem 101. And you did with this kind of delta H of formation. Right, you did it to find delta H of formation. And it's similar to coupled reactions that we did earlier in equilibrium, but at the same time, it's different. The overall idea is the same, but the actual functions are different. So again, kind of what we're doing, what we did with the coupled reactions is you have an unknown reaction and it's made up of smaller known reactions. And so you're going to mix and match the known reactions to give you the unknown reactions. So let's kind of think about the rules here. So this is where it's different from coupled equilibria, is that the rules are slightly different. You'll see what I mean in a second. So let's go with multiply reactions. When you multiply reactions, you have to multiply the delta G as well. So for an example, if you have A going to B, and this delta G right here was 10 kilojoules, if you had 2A going to 2B, you could say, oh, well, what am I doing here? I'm multiplying times 2, right? Multiply this upper one times 2 to get to the lower one. Well, I do the same thing to the delta G, and so then this ends up being 20 kilojoules. Next rule is flip reactions. When you flip reactions, you flip the sign, right, by multiplying by -1, right? So for example, if you have A to B, this delta G is 10 kilojoules. You can write this in terms of equilibrium too. It doesn't really matter. You can see that these two are reverse of this reaction, right? So if you think here, oh, I need to flip this upper one. Well, what I'm doing by flipping is I'm multiplying by -1. And so when you do that, you get the delta G of this second one to be -10 kilojoules. So 1. Cool. And then final rule is add reactions. You have to add delta G's. So for example, if you got AB, this delta G is equal to, let's say, 10 kilojoules, and then you have C or B to C. This delta G will go with 20 kilojoules. Let's go with -20 kilojoules. And then if you had an overall reaction that says A to C, and you wanted to find this delta G, well, you can see that this third one is a sum of these first two, right? When we sum them, B's are going to cancel out because they're on opposite side, and you'll go having A to C. So whenever you sum these reactions, you sum these two, so you add them up, and so overall here you'd get -10 kilojoules, because 10 plus -20 is -10. So those are essentially the three rules. If you think back to Chem 101, you can see how it's similar to coupled reactions. The same thing we're doing to the overall reaction, but the functions we're doing to the delta G is different. I'll post a little review at the end here comparing coupled equilibrium and this Hess's law. So let's see an example, and I'll show you kind of how I would do it. So let's see, in our example, we want to find this. So 3 carbons plus 4 hydrogens gives us 1 C3H8, which is actually propane. Delta G here is unknown. This is what we want, right? So we want to combine carbon as a solid, hydrogen as a gas to form propane. What's the delta G of this reaction? And then you're given a bunch of reactions. So you're given this stuff first, that propane plus oxygen forms carbon dioxide and water. So it's a combustion reaction. So this delta G is equal to negative 2074 kilojoules. Next up, we have that carbon plus oxygen forms CO2. This delta G is negative 394.4 kilojoules. And then finally, we have that hydrogen plus oxygen gives us water. This delta G is equal to negative 457.1 kilojoules. So I just go from left to right to my find. The first thing I see is this carbon here, and I look where else carbon is. There's only one place carbon's at, so that carbon must have come from this equation. And then if we take a look at this one right here, this is a 3, this is a 1. So what we want to do is we want to multiply times 3. So we want to triple it, right? So we'll just write times 3 for right now, and we'll get back to it. Next up in line, oops, I have these 4 hydrogens. So if I take a look at all my equations, hydrogen again only comes from one place. It's already on the right side, so I'm not going to flip it or anything. I'm just going to double it from this 2 to this 4. So times 2. And then I finally have propane coming out. So our propane I see is coming from right here. And so I see that I don't have to multiply by anything, but I do have to flip it. Here it's a product, here it's a reactant. So I multiply by -1 to flip it. So I can say something like flip times -1. And so I'll go ahead and do that. So 3C plus 3O2 goes to 3CO2. This one right here, double 4H2 plus 2O2 goes to 4H2O. And then flipping this one up here, 3CO2 plus 4H2O goes to C3H8 plus SO2, right? And then I'm going to try to sum them up. So let's go ahead and sum them up. Remember, I'm just focusing on these 3 bottom ones that I've manipulated. So let's see, I see, let's go green, I guess. I see 3CO2 here. I see 3CO2. They're on opposite sides, so they're going to go ahead and cancel out. Let's see, is there anything else that's going to cancel out? Yep, we've got this water, another water. That'll go ahead and cancel out. And then I've got this 3 and 2 O2. That'll add up to 5 O2. Which will cancel out with the 5 O2 right there. Right. So what I end up being left with is 3 carbons plus 4 H2s goes to 1 C3H8, which if I take a look at kind of what I was trying to solve originally, we'll see that we're good to go. Cool. It all matches up. And you do kind of want to do these methods right here and sum them up because it's not always going to work itself out. So don't just focus on finding these individual parts. You want to sum them up. Another tip here is that if you see something that shows up in multiple places, like say this C3H8 and showed up here and was somehow over here, and you didn't know which spot it comes from, the best thing you can do is just ignore it, add up the equations, and then try to use some of these up here to figure out what you want. So in the homework, there's some more challenging ones. Overall, this one is quite simple here, but there are more challenging versions of this. And so the same thing you did to the equations due to the delta G's, right? So here we're going to multiply this one times -1, this one times 3, and then this one times 2. And then we're going to go ahead and sum them all up. And if you do that, you get the delta G of the reaction is -23 kilojoules. So that is spontaneous at these standard state conditions, right? Which is generally the degrees Celsius here is the big thing. So this is kind of spontaneous process at room temperature. Final thing, just don't get confused between Hess's law here and the coupled reactions we did in the equilibrium chapter. So if you think about Hess's law, this is kind of the delta H, delta G type of thing. And then if you think coupled reactions or coupled equilibria, okay, we did kind of the same functions, right? We flip reactions. For the delta H, delta G stuff, you multiply by -1. For the coupled reactions, you take the inverse, right? So raise whatever your equation is to the -1, or put it 1 over itself, right? Whereas here we just multiply by -1. When we multiply the reaction, we multiply by the number here, right? So if you double the reaction, multiply by 2, triple it, multiply by 3, and over here in the coupled equilibrium, we raised it to the power, right? So it'd be x to that number. So if you double it, you square it. If you triple it, you cube it. And then here, when we add reactions, we sum the numbers, so we add them. Whereas here, we multiply the numbers. So you can see it's overall the same idea, it's but different mathematical functions. So practice some of the harder ones in the homework as well. This one was quite simple.